what is this enzyme inhibition? So I have put a small animation here. I hope you can see that. I have mentioned here inhibitor in blue color and substrate in red color. So what is happening is substrate is coming and binding, and inhibitor is also coming and binding. So there are two mechanisms you can see. When substrate binding, the product will form, but when inhibitor binds, substrate cannot bind to active sites. That is the active site where the red things are binding. Blue site or blue is the inhibitor where it is binding inhibitor. That means when inhibitor binds, enzyme cannot hold the substrate. That means enzyme cannot form product. So what it forms, instead of enzyme substrate complex, it forms enzyme inhibitor complex. Instead of ES, it forms EI. Instead of ES, it forms EI. EI means enzyme inhibitor complex. So this enzyme inhibitor complex cannot be broken and form a product. But enzyme substrate complex can form product and enzyme can be recycled back. So that is the beauty of normal enzymatic reaction. But in the presence of enzymes, these possibilities are blocked. That means enzymes cannot be recycled and the product cannot be formed and the entire process will stop there for a time being or process may end forever. So both the possibilities are there. It may stop for a time being in some phenomenon or some scenario, or it may end forever in some scenario. So both the possibilities are there in enzyme inhibition. We'll go a little more further about this enzyme inhibition. Yes. So what are these enzyme inhibitors? Naturally, here in the picture, here in the slide, I have put one picture. That means there is a molecule called lactose and there is an enzyme called lactase. Okay. There is an enzyme called lactase. So what it does, lactase hits lactose and convert lactose into glucose and galactose. Glucose and galactose. So what you can do, our body can use that. So the same mechanism you can reduce or you can inhibit by putting some inhibitor there. So inhibitors are doing that role. That means lactose cannot form glucose and galactose in the presence of inhibitors. Naturally, it can form, but here in case of enzyme inhibitors or in the presence of inhibitors, it cannot form because enzyme cannot hold this substrate. Substrate is lactose here. So that lactose cannot be converted into glucose and galactose. This is a simple illustration as well. We'll go and we'll know what is enzyme inhibitor. I mentioned this slide. Enzyme inhibitor is defined as, or enzyme inhibition is defined as a phenomenon which is occurred due to the substance which binds with enzyme and brings about a decrease in catalytic activity of the enzyme. So inhibition or inhibitor means what? Which binds enzyme and decrease the catalytic activity of that enzyme, or else which decrease the rate of or the speed of enzyme catalyzed reaction. It reduces. The enzyme cannot perform in a natural or in a normal way or in a normal speed when inhibitors are there. So this inhibitors binds enzyme. It may bind in the region called active site, or else it may bind somewhere else also. Both the possibilities are there. It can bind the active site or else somewhere else also, some other sites on enzyme. So enzyme is a protein. Protein will have it. If you look at a three-dimensional structure of a protein can have a different site where a different molecule can bind. One major site in enzyme is what we call catalytic site where its substrates are binding and forming the product. So enzyme inhibitor is a substance which binds with enzyme and brings decrease or reduce in catalytic activity of that particular enzyme. So I hope you got the point what is inhibitor, which reduces the enzyme activity. A substance which reduces the enzyme activity are called as enzyme inhibitor. So there are two kinds of enzyme inhibitors. One is reversible enzyme inhibitor. There are irreversible enzyme inhibitors. You might be thinking, what is the meaning of this reversible and irreversible? We'll go and see what is this reversible and irreversible. So first we'll go to important thing called irreversible, because we are not in this slides or in this class, we are not going to study detailed aspects of irreversible, but about irreversible we'll study in the future classes. So I put one simple slide on what are irreversible. So irreversible inhibition means inhibitor binds covalently with the enzyme. I know the difference between the hydrogen bond, ionic bond, hydrophobic interaction, and covalent bond. The covalent bond where the bond is electrons are shared and it's very strong bond. Covalent bond is a very strong bond. So inhibitor binds with enzyme in a very covalent nature. Because of that, what happens? It inactivates them, which is irreversible. You do any circuits or any molecular mechanism there, you cannot bring them back because it inactivates that enzyme. These inhibitors are usually toxic or poisonous substances. The inhibitor binds covalently with enzyme and inactivates them, and which is irreversible or called as irreversible inhibition. And most of these irreversible inhibitors are either toxic or poisonous substances. For example, you take iodoacetate is an irreversible inhibitor of enzymes like papain. So iodoacetate is a chemical. If it binds a papain is an enzyme found in papaya, or glyceraldehyde 3-phosphate dehydrogenase, which is found in human beings. Glycolysis, if you see a glycolysis cycle, that means how the glucose is utilized in the presence of oxygen in a cell, you can see this glyceraldehyde 3-phosphate. So iodoacetate can irreversibly, that means it can kill papain and it can kill glyceraldehyde 3-phosphate. That means it inactivates them. So irreversible inhibition means inhibitor binds enzyme in a covalent nature and it inactivates them and you cannot reverse it. So it is either a poisonous substance or a toxic substance. One example I've given here, we are going to study more than 10 examples in the future classes about irreversible inhibition. And I want to mention one more important example is cyanide. See, cyanide is another element which kills kills us human beings or maybe any animals. How exactly it kills? It binds cytochrome oxidase. It binds cytochrome oxidase in an irreversible pattern. When it binds in an irreversible pattern, you cannot bring that enzyme back to the nature. So the body cannot utilize the oxygen. When oxygen depletes, the vital organ will failure. The same phenomenon happens in when we take some poisonous substance which kills enzyme. But this irreversible inhibitor, there are n number of other applications. So, and there are applications for this, and we'll study detailed aspects of this irreversible inhibition later. But today we'll study, we will learn only two things. What are irreversible inhibition and one example for that. Irreversible inhibition means it binds in a covalent nature with enzyme and inactivates enzyme and it completely stops the enzymatic process. Example is iodoacetate kills papain or glyceraldehyde 3-phosphate dehydrogenase. So we'll go little more further and we'll study the important part of enzyme inhibition that is called as reversible inhibition. So reversible inhibition is a really interesting topic and where we are going to study three important inhibition mechanisms which will clearly tell us how exactly this reversible inhibition happens in the system. So the inhibitor or inhibition binds non-covalently with enzyme. That's a very important thing. If you look at irreversible inhibition, the problem is inhibitor binding with enzyme in a covalent way, in a very strong, in a very high accurate bonding manner. But here it is not like that. It is a non-covalent interaction. If it is a very non-covalent interaction, it is very easy for some chemical mechanism or some molecular mechanism or by using some compound, you can reverse this process. So the inhibitor binds non-covalently with enzyme and the enzyme inhibition can be reversed if the inhibitor is removed. That's very important thing. That means you can remove the inhibitor. So this entire reversible inhibition, so I'm not giving any example here for reversible inhibition. When I talk about the competitive inhibition or non-competitive inhibition or uncompetitive inhibition, there are examples. Those examples you can write it for reversible inhibition. So don't worry about that. I'm not giving any examples here. Any of the examples that I'm giving for a competitive or non-competitive or uncompetitive can be used to represent reversible inhibition. I hope now you got that. The exact idea of what is reversible inhibition. So reversible inhibitor binds enzyme in a non-covalent with nature, and then the inhibition can be reversed if you remove the inhibitor. So this can be further classified into a competitive inhibition, a non-competitive inhibition, and uncompetitive inhibition. All these, there are three parts in this one. So today we will going to study only about a quantitative inhibition. We will study non-competitive and uncompetitive inhibitions in the coming days. I hope now you can clearly differentiate between irreversible inhibition and reversible inhibition. Irreversible inhibition, where it binds in a covalent nature and it inactivates and kills the enzyme. Here it binds in non-covalently, and inhibition can be reversed if you remove the inhibitor. We'll go to next important part, that is a competitive inhibition. So what is this competitive inhibition? Competitive inhibition will happen in a case where, where a molecular mimicry is exist. That's very important. A molecular mimicry. That means if a something mimicking or something else, then there is a chance of a competitive inhibition. For example, I always used to tell in the market, Adidas and Adibas are both look same, but both are different. That means the Adidas market can be reduced by Adibas. But if Adidas push more products into the system, then Adibas will slowly move away from the market. People will come to know Adibas is not original. The same thing is happens here. If a substrate are more, you can reverse this entire process. That's the importance of competitive inhibition. And most of the time, these competitive inhibitors are look similar to enzyme. Sorry, substrate. That's why they are called as substrate analogs. So this substrate, because they are acting like a substrate analog, but it cannot form a product. That's a very important thing here. Substrate can form a product, but competitive inhibitor cannot form a product. So that's why this competitive inhibition has got an important role, one in elucidating the pathway of metabolism. So one important application is you can stop a metabolic pathway at any stage in the metabolism, the process of metabolism. So what you can do is you can trace the metabolic pathway. You just imagine you have a glucose, but you don't have an idea how exactly the glucose are utilized in the body. How the glucose are converted into simple compound in the later part of the metabolism. You just imagine you are using a competitive inhibitor. You are stopping enzymatic the entire process. At each step, you are making that molecule to accumulate. You can extract those molecules and you can study and you can confirm this is the way how a particular molecules are converted from A to B, from B to C. So inhibitor has got an important role in elucidating the pathways of metabolism. Second, this inhibitor, the competitive inhibitor, are substrate analogs, what we so called substrate analogs, can be used as a drug because some of the antibiotics clearly act as a substrate analog. So this substrate analog mechanism could be exploited to treat some of the disease by killing or inhibiting the growth of bacteria. So bacteria has got an enzyme, and bacteria will use the enzymes to survive in a human system. And if you are using a competitive inhibitor as a drug, those drugs will go inside the cell of this bacteria and kill those enzymes, which is vital for the survival of this bacteria. So bacteria cannot cause any further disease in us. So we can cure our disease by using a competitive inhibitor. So inhibitor, which closely resembles real substrate, is regarded as a substrate analog. In a competitive inhibition, the inhibitor competes with substrate and forms a competitive inhibitor substrate complex, and which can be reversed by increasing the substrate concentration. That means it's a competition. If you just imagine you are going for a particular match, you got a 5 people and another team has got a 6 people. Who will win the match? And naturally, the advantage is for people with a 6. The same thing. What is happening here? If your substrate inhibitors are 5 and your substrate is 10, that means there will be a competition happens between the substrate and inhibitor. And substrates are easily can bind to it can bind to the what is called active site because in a competition the substrate will win and inhibitor will lose, and you can reverse this process. In this slide, you can see I have written an equation, a simple equation where enzymes react with substrate and forms enzyme substrate complex, And this enzyme substrate complex further degraded to enzyme plus product, and enzymes are recycled back and it can start the second reaction. But in the second, in the same slide, I mentioned one more equation. That equation is enzyme react with inhibitor and forming enzyme inhibitor complex with a rate constant called Ki. Because why it is Ki? Because it is inhibitor rate constant, and EI is enzyme inhibitor complex. Enzyme inhibitor complex are cannot form a product, but substrate in enzyme complex can form the product. In the picture also you can see there is an enzyme in blue color which binds with the substrate and forms enzyme substrate. If you are putting inhibitor, it forms enzyme inhibitor complex. So enzyme inhibitor complex cannot form a product, but enzyme substrate complex can form the product. So that's the important thing. So it's very important to note that the rate constant for enzyme inhibitor is Ki. That is, we need it for the further this. So what is the example for sub competitive inhibition? This is a classical example of competitive inhibition. What is this competitive inhibition, which can be clearly explained with this classical example? You might have heard about this enzyme called succinate dehydrogenase. This enzyme is famous in one of the cycle in our biological system, that is a tricarboxylic acid cycle. I hope you remember this enzyme, tricarboxylic cycle. But you just have a look on this enzyme. There is a succinate. Naturally, there is a succinate, the chemical compound, which is biochemical compound in us. So the formula is COOH, the two carboxylic groups with CH2 and CH2. So COO, CH2, CH2, COO. And the enzyme called succinate dehydrogenase binds this succinate and convert that into fumarate. So what is the difference between the succinate and fumarate is there is a double bond between CH and CH group in case of fumarate, but there is no double bond in case of succinate. So what I'm doing is in between I'm pushing a mimicking compound. But I always tell mimicking compounds are so dangerous. Same thing here. You can see a mimicking compound called malonate. I'm putting. Because of that, what happens? There will be huge competition between succinate and malonate for succinate dehydrogenase, SDH. So succinate and malonate will compete with succinate dehydrogenase. So succinate can form fumarate, but what about malonate? Malonate cannot form fumarate. Why? Because malonate has got only one CH2 group. It cannot form CH double bond. CH double bond CH it cannot form. So that's why the entire reaction stops there. That's the example for competitive inhibition. So succinate forms fumarate because it can form the double bond. Malonate cannot form fumarate because it has got only one CH2 group. So malonate is a natural competitive inhibitor for a succinate dehydrogenase in an enzyme. So succinate and malonate compete, and succinate forms fumarate if more concentration of succinates are there. But if succinate concentrations are less, I'm introducing more malonate. That means no fumarate will form there. So succinate dehydrogenase will stop at particular stage. So for example, for any reversible inhibitor, you can give example as malonate, the competitive inhibitor of succinate dehydrogenase. I hope you understood what is the the mechanism, not the mechanism, the example for a competitive inhibition. Next part is a little kinetic part. We are not going to solve the equations now, but there is a bit of a kinetic. I need your help, and I'll ask last class what I've done. The same thing you have to do. You may require a small sheet of paper, and then you have to do small work. So we'll go further. I hope now we studied about irreversible inhibition or reversible inhibition. From the reversible inhibition, we took the first class called competitive inhibitor, and we studied what is competitive inhibition, the definition. Next is one example, that is malonate and succinate or succinate dehydrogenase. We'll go further. That is, see, I told there is a kinetics for everything in enzymology. When enzymes are reacting substrate, it forms enzyme substrate complex and it forms a product. But if you put inhibitor, it forms enzyme inhibitor complex, EI it stands. If you plot a graph, a natural graph of a rate of a reaction versus a substrate concentration, that we do it in a Michael-Menten graph. Michael-Menten graph, I'm bringing Michael-Menten graph here. So what happens is, please have a look on this graph. You can see there is a natural reaction which I mentioned blue color line, blue color rectangular hyperbolic curve. You can see, I hope, a blue color rectangular hyperbolic curve is there, which tell us a natural reaction of enzyme with substrate. And there is a red line, that is the same reaction happens in the presence of inhibitor, competitive inhibitors. That means succinate is reacting with succinate dehydrogenase and forming the product, I mean the fumarate, I mentioned in the blue color. Then what I'm doing is, when I'm introducing fumarate to it, so what happens to this reaction? Instead of a rectangular hyperbolic curve, it's slowly turning into a straight line. Not a straight line, I'm telling. I cannot say it's a straight line, but it is almost taking a shape of lesser rectangular hyperbolic curve. Why this change in hyperbolic curve is happening? That means in the presence of competitive inhibition, the Km value will increases. So Km value will increases, but there is no change in Vmax. Initial maximum velocity will stand same for no inhibition as well as inhibition reaction. But the Km value will increases. Is there any significance of increasing Km value? I will ask one of whom I'll ask Akash. I'll ask Akash this question. I mentioned here the Km value increases. Is there any significance of this increasing Km value in the enzymatic reaction? Because we already studied significance of Km. So can you tell me something about this, Akash? Akash, can you hear me? Can anyone else unmute and tell me? Can anyone else unmute and tell me whom I'll ask Apurva.
Yes, sir. Hello. Hello.
Apurva, can you hear me?
Yes, sir. Hello.
Yeah. Can you unmute? Yeah, you are unmuted. No problem. Can you tell me, is there any significance of increasing Km value?
Oh, yes. It's like
Yeah.
hello.
Good. Answer.
Uh, I don't have ideas, sir, but number of substrate molecule it's like
Okay, number of substrate molecules. So because what you are telling is nowhere related to what I was asking. Okay, but you attempted for that. I'll ask whom. I'll ask next. Angelica. Angelica, are you there? No. Yeah. Okay. I don't know. I'm not getting contact with them. So yeah, thank you, Apurva, for answering. At least something you told about Vmax, not exactly about Km. So Km value increasing means there is a increase in Km value decreases the affinity. I hope you remember. Increasing Km value decreases the affinity of substrate towards enzyme. Decreasing Km value increases the affinity of substrate towards enzyme. That means when Km value is increasing means enzyme substrate interactions are decreasing. So inhibitors are taking a role. Inhibitors are increasing the Km. That means inhibitors are increasing the affinity of substrate with enzyme. So substrate with enzyme affinity will reduce, so no product formation will be reduced. So inhibitors are interfering in this one. That is the significance of increasing Km. So increasing Km naturally decreases the affinity of substrate towards enzyme. So V naught versus V naught versus S naught. If you plot our velocity reaction versus substrate concentration, if you plot, you will get what you call a Km Km I have mentioned here. That means increase in one slide I have mentioned Km in a blue color, and another slide I have mentioned Km in a red color. The red means that is increased. It is increasing scale. X-axis it is increasing, so it is shown increase. That means it will increase. So next we'll move further. Now what you want to do here? Do me a favor. Do me a favor. You take one small paper and write Michaeli-Menten equation. Please write Michaeli-Menten equation. All of you who are listening to my class, write Michaeli-Menten equation. Invert that equation as per Lineweaver-Burke equation. Invert those equations like 1 by V naught is equal to Km plus that what is in the numerator and what is in the numerator. You make it ulta. And convert that in the form of y is equal to mx plus c, slope and intercept. Last class, last this thing you have done. I hope you remember. So try for that. So the important thing here is if you invert this equation from Michaeli-Menten equation to this, so only difference is here no Km. So instead of Km, we call that Km as apparent Km. So K dash M you can mention that. K dash M, or else Km with Km there will be extra part, that is 1 plus I by Ki, which will come from inhibitor. So that is the one extra thing here. So 1 by V naught is equal to 1 by S, so Km plus I by Ki. So that's what you call K dash M. Instead of M, you can mention as a Km. Sorry, instead of Km, you can mention as a K dash M. It is because 1 plus I by Ki extra will come. So here, if you plot 1 by V naught versus 1 by S naught, you will get a slope as well as you will get an intercept. That's, I just want to tell you that if you convert this equation into Lineweaver-Burke equation, how it will change. So the only difference between the original Lineweaver-Burke equation and this equation is instead of Km, there will be a K dash M. K dash M means Km into 1 plus I by Ki. So if you plot a graph, versus 1 by V naught versus 1 by S naught, you will get a straight line. You will get a straight line because that equation is for straight line y is equal to mx plus c. I hope you remember. So there are two straight lines here. One straight line is in green color, another straight line is in orange color. So this green color straight line is a normal enzymatic reaction. But when you put inhibitor to this, so what happens? Km is increasing. So how you can say the Km is increasing in this case? There is no change in the Vmax. You can see they are passing to the same point. That means there is no change in the Vmax. Here it is not Vmax, it is 1 by Vmax. Here it is not Km, it is 1 by Km. So in the first case, the Km is increasing. Why it is increasing? It is moving far away from the zero. In the minus scale, if anything, any number move away from the zero, then it is increasing. If it is coming closer to zero, that means it is decreasing. That means, sorry, it is increasing. That means it is reducing its minus value. That means it is increasing. So 1 by Km inhibitor. So you can, instead of writing 1 by Km, minus 1 by Km, you can write it minus 1 by K dash M. So K dash M means Km into 1 plus I by Ki. Km means, so K dash M means Km into 1 plus I by Ki. So 1 by V naught, if you plot versus 1 by S, you will get a two straight line, one straight line for a normal reaction, another straight line for an inhibitor reaction. Normal reaction Km will be the same. So if you compare the normal reaction, inhibitor based reaction, it is increasing. So here intercept is 1 by Vmax and slope is not Km by Vmax. Slope is not Km by Vmax. Slope is K dash M by Vmax. So slope is K dash M by K dash M. I hope you remember K dash K 1 by, I mean K dash M by Vmax. That's very important. There in normal reaction, we mention it as Km by Vmax. But here we are writing it as K dash M by Vmax. So in the